Okay, and these. Okay, so what is smoothing? Smoothing refines the state estimate at some past scan based on future scan measurement. So this reduces the estimation errors. It means uh, as we go scan wise scan estimate at each scan, then it goes back and again is try to smooth, try to purify the state estimate and then again come back here. Okay, suppose your satellite takes some pictures from the earth, then it takes some time to send the pictures to the receiver on the receiver station at the earth station. So before sending it, smooths the pictures with some process the signal after signal processing. It takes some time, then send back to the earth station. Okay,
Yes.
like in the camera we take a photo, but it takes some time to get the output. Okay, so in the signal processing, smoothing is very important. uh, and what is the benefit? Its benefit is it refines. Okay, it refines the trajectory and also it reduces the error. Unlike to other non-smoothing algorithm which try to estimate the target state at each scan and get the status output, that's it, but it do not to refine the estimate. Okay, and compared to non-smoothing type algorithm, smoothing uh, when goes to ahead future scan, then it come back here. Using the future scan measurement, it refines the state estimate. Okay, so smoothing or retroduction is the estimation of a state at time k within measurement interval that is based on measurement up to j greater than k. Okay, so for example, this is interval and having this scan, suppose 1 to k scan, 1 2 3. Okay, so suppose the total scan is suppose 5. Okay, 3 4 5. Okay, so when filter is applied, then the filter estimate this scan, estimate here up to here 5. When you get the estimate of 5, then it goes back and then this estimator tries to smooth this. Suppose this sign is for smoothing. So here conditioning of 5 because you already estimated the scan number 5 state. So here we can write here x smoothing. This sign is for smoothing. Okay, and this for estimate. So here it goes back in the past scan and smooth this like this one.
The case interval is 5.
For example, there are many scans, but it works on some interval. Okay, suppose if there are 50 scans, total number of this total n scan. Okay, but it takes small intervals like 5, and in this case you have to cascade the intervals. If you separate the intervals, then there is a delay, okay, which is not good. So you have to cascade the scan, cascade like 5 scan, then means the each interval is overlapping the other interval. So suppose in this case, if this is scan number 1, 2, 3, 4, and 5, and here again 6. So number 6 scan is overlap to number scan 5. So we have to combine each interval by overlapping method. Okay, and then this thing. So when it arrives 5, then it goes back and smooth this scan. Then this scan, then this scan. Okay. So in this way, the smoothing refine the scan spread in some past scan using the future scan measurement. So what does mean the future scan measurement? It means that the estimator or filter already get the updated scan estimate output up to the scan number 5. Now it goes back to refine and reduce the estimation error. So there are several types of smoothing. First one is fixed point, then fixed leg, and then fixed interval smoothing. And in case of fixed point, the k is fixed and j equals to k plus 1, k plus 2. And in case of fixed leg smoothing, k varies and j equals to k minus l, where l is a leg. And in case of fixed interval smoothing, j equals to n, and the measurement interval is up to n. So for example, this is an example of fixed point. So here the cross sign is points of smoothing. So these are points of smoothing. Okay, and the black dot is available points. Okay, so in case of fixed point, the smoothing point is fixed. So based on this smoothing point, it smooth the other points like this one. If we smooth this scan number 2, because in the fixed point smoothing k is fixed. Okay, so then j equals to k plus 1, k plus 2, k plus 3, and so on. So like in the next scan, based on this, the number 3 scan will be smooth, and then this is k plus 1, and this is k plus 2, and this is k plus 3, and then this, and then this. Okay, this is the fixed point. After first scan, then second scan smooth. This is fixed scan smoothing. Then based on this, the third scan obtain, fourth, fifth, sixth, and so on. Okay, and in the fixed leg, so fixed leg is different from fixed interval. Fixed leg means J is a smoothing point. J is a smoothing point, and K is a scan. K varies. K means vary 1, 2, 3, 4, 5, like this one. Okay, and minus L. L is a leg size. Okay, how many scan are lagging behind the K? Okay, how many scan are lagging behind the K scan? So if K is 2, leg is 1. If leg size is 1, then J equals to 1, and so on. If K 3, then 2. If K 4, then 3. So if we smooth here, based on this, if we are here k is 3, the 3 minus 1, this is smooth. Okay, if k is 4, 4 minus 1, the 3 scan is smooth. If k is 5, 5 minus 1, then the j equal 4 is a smoothing point. Okay, so for example, these are available points. Okay, suppose this is 1, 2, 3, 4, 5. So what happens in the fixed leg smoothing and fixed interval smoothing? Fixed leg and fixed interval. Two types of filter is applied. Okay. First one is forward filtering. This is forward filtering. Okay. Here the state estimate, like the filter will estimate scan per 1, 2, 3, 4, 5 here. Okay, like you have done the Kalma filter. Okay, in the previous lecture. So the forward filter will get the prediction like k plus 1 and estimate k up to k, like this one. So the forward filter will get these two data for each scan and arrive here like this. This prediction k plus 1 estimate here. Okay. Then for the fixed leg, smoothing, then it goes back here after filtering up to number 5 scan. Then it goes there here and it smooth only this one. It smooth only this one. Smoothing. Okay, fixed leg. Okay, so after smoothing it gets the state like this one. Okay, and this we said that up to here another interval will overlap here, because suppose we have total number of scan 50. So we cannot like do this continuously 1 to 50 and then goes back for smoothing. It takes a lot of time. So we work over the small interval like subset. Okay, because when satellite take pictures, so the Earth station will not wait for the all pictures. If we want to see the map of some area like this one, we can get just search and we can get at once. Okay, so so the satellite will take a picture and send continuously sending the picture. So when satellite take one picture, then it takes some time so that it smooth that picture and process the signal and send immediately back to the Earth station, and then second picture and then third picture, fourth picture. So if 50, then we have to work the small intervals like this, 5, 10, and then 50, and then 20, So in each scan, we do some power filtering, then go back and smooth, and again. And so for the next interval, it has to be overlapped, like this one. The other, and the other scan will be overlapped here, 6, and then 7, 8, 9, and 10, like this. Then again, this start from here, 6 to 10.
5 and 6 same point.
Not same, but it use this measurement and this measurement to get this estimate, like k plus 1, this is 6, this is 5, and this is 6, two measurement, and to get the 7th prediction, like this one. Okay. And in case of fixed interval, the interval is fixed, means you have available point 1, 2, 3, 4, 5. Okay. So using the 5 available points, you smooth the each scan one by one, like okay, up to power filter. One, two, three, 4, 5. Okay, so you have, like in this case, and you have already estimated all these scans. This is estimator. Okay, so you have already estimated all these scans. Now, in this case, it will go backward tracking, to backward filter. Backward filter means two types of filter in this case: forward tracking and then backward tracking. So this is the for forward tracking. Okay, and the backward tracking, like this. In the backward tracking, the last one is the same to this one. So because in the backward tracking start from this one, from here to here. So this estimate, forward estimate, is equals to the backward estimate. Okay, because we are starting from the same scan, so the first scan will be the same. Now the fourth one is the fourth condition on 5, and then 3 condition on 5, and then 2, 5, and then 5. And then it fuse the data, the forward data and the backward data. Okay. Fuse means add. It will fuse the both forward prediction and the backward prediction. Suppose this is the okay. suppose this is the result of the fuse prediction, and then it will smooth. This power filtering here, and then backward filtering. Suppose this is F is forward, this is B for backward. Okay, here B for backward and F for forward. Okay, then it will fuse. Figure state like, suppose this is some other simple capital X. Okay, capital X is a fusion, so it combined like this one. Okay, and after the fusing, smoothing is applied. So now each scan will first fused and then smoothing applied. Okay.
Low favored filter is last 1 by 2.
One condition on 2. No, one condition on 1.
And left side smoothing rotation. Yes. X 1 bar.
One condition on 1/5.
5 is interval.
Yeah, total scan 5. 1/5. Okay. So again, you have to note here that this smoothing is relevant to the offline estimation problem. Okay, because it gets some delay. Because when we estimate up to here, then we have to go back here. Then first we will fuse, then we will do smoothing. It takes time. Then we first fused each scan, then smooth each scan. So due to this time, due to this delay, we cannot use this type of problems in the real-time application. But in some application which can tolerate some delay, we can apply the smoothing. Okay. Like for example, I have applied the smoothing in my experiment. Like I performed the tracking of the UAV. So in my case, it works perfectly. So that was no problem. There was no problem. But those applications of the real time which can tolerate some delay, then you can apply the smoothing. So let's see the derivation. So when we see the derivation, then you can understand everything. So main is the forward filtering, and then backward filtering, and then fuse and smooth. Note the length of the interval. Okay, suppose there are 50 scans, and you have decided that in the 50 scan we have divided the length of 5. Means 5 scan, 5 scan, 5 scan. So suppose n is a size of interval. So each overlapping interval size is 5. Okay, suppose it's 1 and 50. Start from one scan and end to 50 scan. Then here 5 interval. Okay, 5 interval. We do forward filtering, then backward filtering. 1, 2, 3, and 4, 5, and then fuse and smooth, fuse and smooth, fuse and smooth. Up to here. When we arrive here 5, suppose we have applied fusion and smoothing from 1 to up to here. Then we have to discard here, discard one scan. Suppose we have discarded discard, because we have already calculated the estimation, smoothing estimation up to 5. Then we can discard this scan and add one more. We have add one thing, 6. So again the length is 6. Again length is 5. 1, 2, 3, 4, 5. Okay, if there are 5 here, 5 here, okay, this is already smooth. We have already get the smoothing. Then we can remove and add another from here. So again this becomes under another 5 length. 1, 2, 3, 4, 5. Then and in the next cycle we remove this one and add from one more. Then again 5. So this way we can, this is called overlapping. This is called overlapping because the first length is 1, 2, 3, 4, 5. We have done power filtering, then backup filtering, and smooth this one. Okay, we have already get the smoothing estimate of this scan. Then remove it and add one more, and you can get the same length of 5. So here in this case we have overlapped the interval like this one. Okay, so this is if we move 1, then add 6 1, then again the next interval is 2, 3, 4, 5, 6. And similarly in the next cycle remove and add 7. Then again this is length of 5, and so on. Okay, so this is called the fixed leg. This is called the fixed leg. Why this is called the fixed leg? Because we only remove the one, and suppose this is K. Okay, then if we add the one scan, then this is lagging, the J leg. This is called the fixed leg. Okay, suppose in other case 1, 2, 3, 4, 5, 6, 7, 8. Suppose there are 32 scans. Total number of 32 scans. We divide the interval by 8. So each interval length is 8. So this is a fixed interval case. So in this case there are 8 scans in one interval. Then forward filtering, backward filtering. Then we smooth. Suppose 1, 2, 3, 4. We smooth this one. 1, 2, 3, 4. 4 scans smooth it. Okay. Then discard. Then discard. statistic calculation. So we can discard this thing for statistical calculation because we have already smoothed this scan, and then add 4 more scan like 9, 10, 11, 12. So this is again 8 length, and it's also 8. In case of fixed leg, we do only one scan smooth one scan in each scan, in each interval. In case of fixed leg, we smooth on one scan in each scan and in each interval. And in case of fixed interval, we smooth for fixed interval like 4, 1, 2, 3, 4.
Leg 4.
Huh? No, this is not leg, this is leg. Like this. Like this. Smooth, add more. Smooth, add more scan. And smooth, add one more scan. And in this case, this is fixed, like this one. Then smooth 1, 2, 3, 4, 5, like this one. Okay, after smoothing, separate this thing and add 4 more to get the overlap interval. Okay, so we can remove 4 chairs and add 4 more chairs here. Okay.
Then how to decide for the case interval?
This is series. Okay, like 1, 2, 3, 4, 5, 6, 7, 8, up to 32. Smooth this one and separate. Then add 4. See, in series, add 4 more. Then again, this is the length of 8. 1, 2, 3, 4, 5, 6, 7, 8. Then again, smooth this first 4 and separate this thing for statistics calculation and add more 13, 14, 15, 16. Again, length is 8.
Can 6 point remove one calculation?
6 point?
Yes. 1, 2, 3, 4, 5, 6 remove, and 7, 8, 9, 10, 11, 12, 14.
You mean
Now,
yeah, 1, 2, 3, 4, 5.
Yeah.
Smoothing, then remove
Now we remove 4 points,
4 point.
but we can 6 point remove.
6 point.
Yeah. Remove, able to remove. Now we remove 1, calculate 4, then backward, remove 4 points,
Yes.
but 4, then backward process, and 6 points remove.
Each point remove. Yes.
Able to.
Yes, sir. Okay. Because we already get. This means we already get the estimation of 4 scan. Okay. Remove does not mean that it is not useful and you have to remove. No, it is useful. You get the smoothing estimate like this one. Okay. Then this will go for the function for statistics calculation. Okay. like state update, like RMS calculation, okay, and trajectory. Okay, and to generate a updated trajectory, so uh, this will go to another function for static calculation. Okay, and uh, and uh, and consequently you have, and simultaneously you have to add more scan, so it can smooth another interval, and it will go to for this function and add more like this one. Okay, clear?
Okay.
So discard means you. It does not mean that it is not useful and you are just removing. No, it means you already calculated smoothing. Means you have already calculated the result of the first 4 scan of each interval. Okay, for RMS calculation and trajectory calculation and false strike discrimination calculation, like this one. Then adds more. So among them, fixed interval smoothing is most useful. But you can use fixed leg, because fixed leg have a small delay. Fixed interval has more delay. This is because in the fixed interval we smooth 1, 2, 3, 4. Each time we smooth 4, and each time we add 4 scan. But in case of fixed leg, we smooth 1 scan and 1 add, then 1 scan, 1 add. This is even more good, less delay. Okay, but it takes a little time, so we can. It is difficult to apply fixed interval for the real time application, but we can apply this one. Okay, so, and this is your assignment. Okay, all same. All the students have same assignment, so you can work together. Your assignment. This is your first assignment. Fixed interval. Smooth. So you can apply this algorithm to your gamma filter. Okay. So there are two types. There are two ways for fixed interval. One is the using by some formulas. This is very easy and convenient. So one is known as two-pass filter. Two-pass filter. Okay. Here we use the branch, trunk, stripe rule. algorithm, RTS. This is very famous algorithm. So most people use this in their application. So this is widely used in the literature. And other type is the forward backward filter. This is what I have explained before. Forward backward filter, and this is the two pass filter. Okay. So in this case, we first go for the forward backward filter. So in this case, we have to obtain first for forward filter. Okay. And in this case, the forward filter estimate, like here f is forward, is as expectation for xk, okay, z k zk plus 1 and up to zn. Okay. First you have to apply the forward filtering, and you have to estimate each scan based on the measurement k. Okay. So first you will apply like this one. This is the scan, and this is the estimate. Okay. So using 2 point, you have to initialize number 3 scan. Okay. Here you get the prediction. For 2 plus 1. So this will here x of 3. This is the prediction, and this is estimation. This is different. Okay. At here you have to apply for comma filter prediction. So it will get the x of 3 here, and using this you have to update x of 3 using the z3. Okay. So when you obtain estimation of x of 3, then you have to propagate this for number 4 scan. Okay. And also and for the next time scan, you have to again use the 2 point measurement for the initialization. You have to use the scan number 2 and 3 measurement and initialize the other new track and get the prediction for x of 3 plus 1 with 4, like 4, x of 4. Okay. Then update this thing based on z of 4. Okay. Based on z of 4, and so here apply the comma filter estimate to get the 4. So here you have estimate estimate in each scan based on each scan measurement, the forward filtering. Then suppose this is a B, the expression x of B condition on z a plus 1 zn. Okay, and the respective covariants like F, K. Here covariants B, K. So in case of forward filtering, forward filtering, your F matrix is same like this 1 T 0 and Q is same. Okay, so this will add the velocity information to the current state. Okay, but in case of backward filtering, this is reverse, like inverse. Okay, like this one, minus t, because when we go reverse, then your time will be reverse. Okay, and same Q 1/4 minus t here on minus t. Okay, but your measurement matrix is same. Okay, this is the same in both cases because this just select the position measurement from the estimate. Okay, this is 4/1. Then when we multiply this thing to this thing, you will get the just position. Okay, so you have to remember this thing. For backward filtering, you have to use the minus sign. So in this case, your backward propagation is like F inverse SKB. Okay, F inverse and process noise VK. Okay, so and when you use the Q, so Q is the same in the forward filter, but in case of here with the backward filtering, your Q is F inverse Q and F inverse transpose. This is Q for forward. this Q is for forward. Means this is this Q, and again transpose. This is QB. Okay, so this you have to use this in the comma filter. You have to use this in the comma filter. Okay.
Same value about.
No, this is different. You know the formula for the comma filter? We use the Q value in this one.
Why notation same?
The comma filter like prediction x k f k plus 1, like this one. So in case of backward you have to use this one, and for covariance so you have to use this one, h ph and plus qb. So this qb is this one here. Okay. Yeah. This could be is this one. So now how we apply the fusion. How we apply the fusion. Okay. This is very simple. The pop filter you have already applied in your mid exam. Okay, when you do the backward filter, you just reverse the time. And then for fusion, suppose we are fusing, then this is a static PK forward, inverse, and state estimate forward. Okay, this is clear. X plus backward covariance at scan K inverse B K, where the PK is equals to forward covariance inverse plus backward covariance inverse and whole inverse. So this is the fusion. Okay. For power filter, you will get the this state and covariance. Okay. This is your gamma filter, forward gamma filter, state estimate and covariance. and from vector filter you will get the backward state estimate and the backward covariance. Okay, then you have to add plus and multiply this thing with this matrix, inverse covariance matrix. And in this covariance matrix we have added the covariance of the forward and covariance of the backward. Okay, and finally we have to update this information. We have to update this and this, like command filter update this thing K and P static K. Okay, and this is Z. Suppose we are at scan number 3, then 3, because first two scan are used for initialization, so there is no data in the first two scan. Then Z of 3 and H R. Okay. So here you get the smoothing output.
And is
Yeah, N is this thing. So interval suppose there are n measurement in the interval, like Z1, Z2, Z3 up to Zn. So there are, suppose there are you have estimated the object state conditioning on Z of 1, Z of 2, Z of 3, Z of 4 up to Z of n. So main thing is the fusion and smoothing. Okay, how do we smooth and how we do apply the fusion? Before this you have to filter forward and then backward. So when you go the backward, this is for loop, for forward, and then for -1 M2 here backward. Okay, so here this is not 1, this is K. K scan. Suppose K is 5, the 5 goes to length of 8. Then similarly this if any length of the scan, and then go back to K. So in this case, is first scan of interval. This scan is the last scan of interval. Okay, for example, one, two, three, four, five, six, seven, eight. In this case, your K is 1. This is K, first scan. And your N is this one. Okay? When you smooth the first 4 scan and remove and add 4 more, then this is your K and this is your N. So this column will change like 5 to 12, 5 to 12, and then in this interval when you smooth this one and add more 13, 14, 15 and 16, then in this case your 9 is K and 16 is N. So again your interval is changed by 9 to 12 and 9 to 16 and 16 to 9, like this. Okay. So this is your assignment, and the other method is the 2-pass filter, the RTS smoother. Is in the same way, but it is used to calculate the backward prediction with a formula, not the backward tracking like this one. So it is you can say easy because it takes less time, because it do not go for the backward filter. It just use for formula to calculate the backward prediction, but it's something different. Okay, so you can do this way, like this one. Okay. And if you have any problem, then you can come to me, and you have done. You can stop the recording. Okay, otherwise, because your class is end. So